So to achieve Catherine's science goals, we want to detect X-ray emission from black holes. But X-rays don't get through the atmosphere, so that's only possible if we get into space. So that's a good example of astronomy that can only be done from space. There are other kinds of astronomy which, while not impossible from the ground, are really much better from space. We can get sharper pictures in space, and we can get deeper pictures in space. So we've a lot of motivation to get up into space. Unfortunately, astronomy from space is not easy. A lot of the things we think are simple on the ground turn out to be much more complicated in space. Okay, the first thing we've got to do is get up there, and that's why we need rockets. Now, most of a rocket is simply fuel. Even to get into low Earth orbit, 90% of the mass is propellant. Now, that fuel costs money, but it's not just the fuel that costs money. To launch a rocket, you need a lot of infrastructure. You need a mission control center, you need a launch pad, you need test facilities. All this involves equipment, buildings, people, and all those things cost money. It's a very complicated business getting something up into space. Now, we have to then rely on an existing space industry, government space infrastructure in order to do astronomy from space. This is very different from ground-based astronomy, where we're used to the idea that we can build our own observatory, and that may be complicated and expensive, but then we can look after it ourselves. Working in space, we have to work with the infrastructure. Now, the next problem is that even in low Earth orbit, we're really only just creeping up into space. Let me show you what I mean. So, if this is the Earth here, the radius of the Earth is about 6,370 kilometers. That's an average because the Earth isn't quite a sphere. Low Earth orbit is at a height of about 500 kilometers, or maybe a little bit more. So it's really only just creeping above the surface of the Earth. Now, if you imagine a spacecraft here, a star up here it can see quite easily, a star down here it cannot see. Likewise, it's a problem for it to speak to ground stations. We'll come back to that later. So low Earth orbit is not ideal for a variety of reasons, and we'll see in a moment how we can get further away. So the next problem is power. There's no electric sockets in space, we have to make our own power. So that's why most spacecraft use solar panels, and to gather enough power these can be pretty big. This picture you're looking at now is the solar panels for the Dawn spacecraft, which are currently under construction. You can see how big they are. Now, much larger in fact than you can fit into a payload of a standard rocket. So what you have to do is put them inside the payload folded up, and when you get into space they unfurl. So easy enough in concept, but very tricky to do in practice. So the next problem is pointing, or attitude control. Now, anybody who's seen the movie Gravity has seen Sandra Bullock spinning out of control, and indeed in space it's extremely hard to control your attitude. But for a telescope this is a big problem. We want to point in a very specific direction to look at a specific star, and we want to keep very still and not wobble while we point at that star for maybe hours at a time. So we need precise 3-axis pointing and stabilization for astronomical telescopes in space. Now, in fact, there's two things you want to do. You want to be able to change your position to move around the sky, and you want to be able to sense your position to tell where you are. So first of all, let's talk about altering your position. So the obvious way to do this is with little gas thrusters, and that's the sort of thing you see astronauts doing in the movie with their own bodies. And spacecraft do that, but there's a problem that you can run out of gas and that limits the lifetime of a mission. There are other ways to change your pointing. You can use momentum wheels. So these are spinning wheels that you can spin up and down using a motor. And if you have wheels in the 3 different directions, then you can make the spacecraft rotate. Another cunning method is so-called magneto-torquers. You have a coil, and you pass power through the coil and it interacts with the Earth's magnetic field and tries to line up with the Earth's magnetic field, and you can use that to change your position. So that's changing position, but you'll also want to be able to detect, to sense where you are on the sky to tell if you're pointing in the right direction. So there are a few different ways of doing that. The simplest way is to look for the horizon. You can see where the edge of the Earth is from space. That's horizon sensors. It's also pretty easy to detect the sun, so you can use sun sensors. And again, they're quite crude, those methods, but important. You can use gyroscopes, or to get really accurate answers, you can use star trackers, little cameras that have in them maps of where the stars are, so that you can tell exactly where you're pointing. Now let's talk about the space environment. Space is not empty. In fact, in some ways it's quite a hostile environment. Mostly so because of high energy particles which pervade space. Now these have a variety of sources, but most of them come from the solar wind. They've come from the sun, they travel across space, they interact with the Earth's magnetic field, and then they stream down towards the polar regions of the Earth. And then when they hit the atmosphere, they excite atoms in the atmosphere and cause a glow. That glow is what we see as the aurora, the northern lights or southern lights, depending on which hemisphere you're in. Very pretty. Here's an example of an aurora seen from the north of Scotland over Thurso Castle. But to astronomers, just a nuisance. Now, the radiation is not uniformly spread around the Earth environment. It comes in two particularly tense so-called radiation belts. Let me show you. So if we imagine the Earth here, then at about 1.5 Earth radii from the centre is the first of those belts. So that's at about 1.5 Earth radii. And then out here at about 4 Earth radii is the second intense belt. These radiation belts, sometimes known as the Van Allen belts. So one good place, you want to avoid these radiation belts, okay? So one thing you can do is to stay in low Earth orbit here, and that's one reason why low Earth orbit is popular. Or you can get in between these two radiation belts, or if you can afford it, you go beyond the radiation belts out here. Now, as well as the particles, the other problem is debris and dust. So debris means things that we put up into space and are left behind. Dust is naturally occurring, small particles, the same small, tiny little rocks that cause shooting stars that we see in the sky as they hit the Earth's atmosphere. But they can also hit our spacecraft. They carry a lot of energy, so even though they can be very tiny, they're moving very fast, tens of kilometers a second, so they can cause a lot of damage. Here's an example. This picture here is the window of the space shuttle, and it shows a pit in the glass caused by an extremely tiny piece of material which hit the space shuttle. So the next environmental problem is heat. Now on the Earth we're used to the way our weather system, the motion of the atmosphere, redistributes heat around the globe and smooths things out. But when you're in space, solar heating is a big problem. Basically, towards the sun you have a very hot side, and on the other side it can be very cold, and you get severe thermal stresses. So this is why a lot of spacecraft use solar shields. If you look at this picture of the James Webb Space Telescope, which is the successor to the Hubble Space Telescope, currently under construction, the plan there is to use an absolutely enormous solar shield. It will be about the size of a tennis court. So that's what's in this picture here. But as well as solar shields, it's one reason why a special orbit known as the Lagrangian point is very popular with astronomers. Let me show you how that works. Imagine here we have the Earth, and somewhere a long way over here we have the Sun. We draw a circle round here, and at this point here known as the Lagrangian point, the force of gravity on that due to the Earth and the force of gravity due to the Sun balance out. So this is a kind of equilibrium point. Now, in fact, if you go the other side of this circle, there's another point here where this is also true. That's known as the first Lagrangian point, L1. That's known as the second Lagrangian point, L2. This is at about 236 Earth radii, a long way out, way past the Moon, and it's about 1% of the way towards the Sun. Now, these Lagrangian points, they're very cool for two reasons. The first is that because they're gravitational equilibria, a spacecraft can just kind of hang there, sort of hover. But the other reason for this one here, L2, is if you're sitting here, the Earth is shielding you from solar heating. So at L2, it's much easier to keep thermal control. You reduce those thermal stresses, but also you can keep your spacecraft very cold. And because of that, it's very popular with infrared astronomy. So the next problem is data. There's no internet in space, but somehow we've got to get the data back to the ground in order to use it. So the way we do that is we've got to beam the data down from the spacecraft to a radio dish somewhere on the surface of the Earth at a ground station. Now, this is one of the problems with low Earth orbit, because if you imagine yourself here at a ground station, you're watching a spacecraft which is going overhead. You can only see it for a small fraction of its orbit and then it's disappeared. So either we have to dump all the data very quickly to that ground station, or we have to use a whole network of ground stations all the way around the Earth to stay in contact with it. So one of the solutions to that problem is to get high up into a special orbit known as geostationary orbit, where we can be in contact with a single ground station the whole time. So that's how we do space astronomy. Now, what are the pros and cons of doing astronomy from space as opposed to from the ground? First, let's look at the pros. There are three biggies. There are some types of astronomy which are impossible from the ground: X-ray, infrared, ultraviolet. So that's a big advantage. There's no other way to do it. The second advantage is that we can make much sharper pictures. That's probably the biggest single reason why the Hubble Space Telescope was sent up. The third advantage is we can take much deeper pictures. We can see faint things very quickly by avoiding the glow from the atmosphere. So those things are very important. All right, so what are the disadvantages, the cons? Well, there's one big con, that is that it's very, very expensive. It's much more expensive than doing astronomy from the ground. There's a second disadvantage, which is that you can't fix things if they go wrong. Well, I say that, but of course famously the Hubble Space Telescope was fixed. Astronauts went up in the shuttle, replaced some of the optics. You can see that happening in this picture here. However, that's unusual, and to do that, to be able to fix things, that costs a lot of money. So really we're back to disadvantage number one. It's very expensive.